Hi, my name is Bill Fortney, and thank you for being here for the last part of this series on statistics for engineers, where we're looking at design of experiments and how we really go about pulling data out to answer our engineering questions. And we started off with just seeing that design of experiments is what gives us the foundation to be sure when we are questioned on information that we pull from the real world to make a decision on, so that we know that we can sleep good at night, that we have solid information, and we can answer all the questions from our senior engineer who's asking, are you sure about this? Did you think about this? Did you consider that? And we saw the process that we have a question of a thing of interest in the world. We're going to design the experiment. We're going to check it for validity. Then we're going to be a detective and see what we can learn about it. And as we do, there's three basic questions that we're going to be asking. What can I expect? Does variable A impact? Is set A the same as set B? And then when it is, and it's a mathematical independent variable, coming up with what that relationship is. And we also saw that this was the same process that you've seen are going to be using in lab, where we've got these three steps, and here are these same three steps in this process that you're seeing there. And step number one, you've got this sheet right here to guide you through it and the DOE guide. Step number two, we've seen in video number 8, where you're going to plot the data in run order. You're going to sort it and look for any non-randomness happening before you use the data. And then step number 3 is really what we're bringing in right now. So I first want to hit just the highlight of what we're going to do. Whoops, we go back when we're looking at the data. First, you're going to be looking at it visually, all different ways, changing the channels, and a few tips. One, use your engineering knowledge. You know about some of the fundamental principles of what's going on in your experiment, and use that to predict relationships, and then arrange the data to explore that. Be curious, be a detective, listen for what the data is telling you. Sometimes you're going to have to manipulate the data. Like you may be wondering the accuracy of a device. So instead of looking at the actual numbers you measure, you're going to subtract it from a standard and you're going to look at error. You're going to be able to see that a lot different. Sometimes the absolute number works well, sometimes percent difference. You're going to have to try both. The point is, use your engineering knowledge and manipulate the data in a way to tell you what you're talking about. Once you know your repeat measurements are random, you can average those and eliminate some of the massive data. Once you know an independent variable doesn't impact, remember you can average over that. We're going to see that again when we review how we handled the set A and set B the same. And then number 2, is this data the same or is it different? That's what this video is really going to focus on. And if you remember, we had the basic approach to that. That was question number 2, where we said, okay, here's what we're going to do. We're going to design our experiment. So the only difference between the two groups is the thing that we changed, our independent variable or variables. Then we're going to look at each grouping to make sure that it's only random. Then we're going to look between the two groups and ask ourselves, is this between difference due to randomness? Is it one population, or is what we're seeing a special cause that's not explained by one population? And based upon what we find there, if we find that what we see is explained by random variation, it's just common cause, there's no impact, we can combine those and summarize it with one average standard deviation. If we find, yes, there is special cause there, then we can't. We have to summarize each level of the independent variable independently. And then we added this one thing in here in terms of our approach, where we're going to have multiple variables that we've looked at, and we're going to regroup our data in all those ways, being curious, looking at all those variables. And as we learn, we're either going to eliminate factors, meaning we combine the data, or we're going to keep them separate because they really did matter. Okay, one thing we didn't hit when we were talking about this that I want to hit now is why randomization is so important to knowing that the only difference between the two samples is what you changed. So let's go back to this finding the ultimate. And let's say the vendors are independent variable. We're changing that. We have two vendors. The heat treating temperature, it might vary some, so we measure that. The forge pressure, there's separate settings that we can use, and we picked one and we're holding that constant. The rest of these, we can't really do a whole lot with them. And so those are called nuisance variables. They're just kind of hanging out there. We know they're there, but there's really not much that we can do with them. Okay, so now imagine that we have perfect knowledge and the impact of these nuisance variables. Let's say that the temperature in the plant is rising all through the day. And because of that, these nuisance variables influence our ultimate like this. It makes it rise. Now, what this is graphing is the ultimate is up here on the Y, time is going across this way, and the thing I want you to get in your head is nothing is making ultimate change except these nuisance variables. So here was ultimate at the beginning of the day. Our ultimate is rising all day just because of these nuisance variables. Could that happen? It absolutely could happen, because remember, there are so many things affecting whatever it is you're measuring. Now imagine that we don't randomize. We take all vendor 1 data, then we come in and take all vendor 2 data. And I hope you're looking at that seeing, wow, wait a minute. All the data for vendor 2 is going to be high, not because it was vendor 2, but just because it was taken later and the nuisance variables are making it rise. That's right. So if we looked at our samples that we took, if we pulled it out and we graphed it, it's going to look like this. Not because vendor 2 mattered. Remember, nothing changed. Ultimate only changed because of these nuisance variables. It is higher because of how we sampled and because things were changing over time. The difference between samples in this graph is due to the impact of nuisance variables. If the vendor made a difference, it would be on top of this, but it would be confounded. That's a statistical term we use. It would be confounded with the impact of these nuisance variables. So instead, this is what we're going to do. We're going to randomize our readings all across the entire time period. So let's say we're going to take 10 readings of each vendor. We would go on the paper and put 1 through 10 and put vendor 1. We would put 11 through 20 and put vendor 2. We would assign a random number to all of those. Then we would sort the random numbers in ascending or descending order. So now all of a sudden, which vendor material is going through the factory when is random. So what we've done is we've spread each vendor's material randomly through this time period. So the effect of that temperature change, we've spread across both vendors equally. Nobody got penalized like over here, vendor 1, vendor 2 got penalized because of the change. We spread the love. We shared the love across everybody. So then if we took data like this is what it's going to look like. Notice the effect of temperature would be in both data sets. So what's the only difference between the data sets? Which vendor it is, because they both have the impact of those nuisance variables changing. Now, the nuisance variables usually don't change like linear like that, but they affect things over time. So by randomizing whatever effect those other variables are having, we're doing the best job we can to spread their impact evenly over the other factors that we're changing. That's the best that we can do. Is it possible they change in a way and still impact one a little bit more than the other? It is, but it's a low chance. So this is why randomizing, when you take data, is so critical to knowing, okay, is set A different from set B? Okay, so this number 2 right here, is the data different? We're going to spend the rest of the videos looking at how we tell. But I want to hit this last step in terms of exploring, observing, drawing final conclusions. You're going to pull it all together and say, okay, what factors matter? Did heat treating matter? What value can I expect for X? What is the relationship? And I want to highlight, be careful about statistical difference and practical difference. The statistics may tell you there's a difference between A and B, but the difference is so small for the decision at hand that practically they're the same. So don't get wrapped up in the math. Oh, they're different. Yeah, but practically speaking, they may not be. And then the last one, which is critical. That's why I want you to hear this. You need to be asking yourself, under what conditions do my conclusions hold? And this jumps back to when I was telling you what we really focus on with this first question, what can I expect out of you? It really goes down to is what happened during sampling, the conditions you care about for your decision. You need to design your experiment so that's the case. So when you get finished analyzing the data, you need to double check your conditions so you know what can I really say. And the best way I know to show you this is with an example. So you remember what we do with variables. When you design your experiment, you're going to intentionally change them, you're going to hold them constant, you're going to measure them, or you're going to randomize them. You try to identify all the variables you can. The ones you just can't do anything with, those nuisance variables, you're going to cover with randomizing. So now let's go back to this one and remember the vendor we held constant, heat treating we measured, these guys were nuisance and we held that guy constant. So let's say here was our findings. The heat treating temperature was approximately constant during the entire experiment, so not a concern. What's the difference between the two data sets? Vendor, heat treating temperature didn't matter. The data collection was randomized for vendor, so they were all spread out. We spread the love. So the impact of the nuisance variables was spread equally between vendor 1 and vendor 2, so that's not a factor. And then when we plotted vendor 1 and vendor 2, it clearly showed a special cause change. It wasn't random. The vendor does matter, and vendor 1 produced a lower ultimate. Great. Now I'm going to ask myself, what other variables may impact my findings? Well, this was one batch of material from each vendor. Would other batches show the same results? I don't know, because I only had one batch of material from each vendor. What if I get some more material in from them next week and redid the experiment? Would I get the same things? I don't know, right? If it was important for you to know, then you should have designed your experiment to have multiple batches. Remember, do the conditions of your sample reflect what you need to make your decision? I don't know. Something else. How about the forge pressure? I'm making this up, we have 3 different forge pressures that we run at for different reasons. We held that constant at 1 forge pressure. Would I see the same thing at other forge pressures? I don't know. Do we always run grade 8 at that pressure? No, we sometimes change it. Okay, so now, what do I really know then? This is the piece. This is what you want to get in the habit of asking yourself. What do I really know so I don't oversell what I've learned? Here's what I know. At this forge pressure, the batch of material supplied by vendor 1 had an ultimate tensile strength lower than the batch material supplied by vendor 2. That's all I know. I can't branch out any more than that. If I need to know more, then I need to do some more experimenting. And that's okay. Quite honestly, most of your experiments as an engineer are going to be in steps. You do a little bit, you learn, that tells you what direction to go next, you step and you go in that direction, okay? But I just wanted to highlight down here, step number 4, it's important. Look, does my sample accurately represent the population? That's asking the conditions I care about for my decision, did I replicate those conditions in my sample? Or are there other things I need to explore and change before I can make the broad conclusion I need to for the decision I'm making? Okay, so now let's jump in and start looking at these tools to figure out, is this data the same or different? Because like I said, data is our bread and butter. We need to know that information before we can come down here and start drawing conclusions. And the first way we're going to do it is just visually. We're going to graph the data grouped by the variable that we're interested in. And a lot of these I show too. You could have as many as you want. And I'm going to be asking, is the variation between one the same as variation between the other? We're kind of assuming that the measurements are normally distributed, and We're thinking of a confidence interval. When we've been saying plus or minus 1, 2, 3 standard deviations, the average plus or minus those, that's called a confidence interval. You're going to hear that term. So we've been kind of an imaginative confidence interval and saying, okay, if this was my population, would I expect that? That's this tool, okay? So it's pretty straightforward. You've seen it before. I'm just going to review that here. So we're asking, is set A, we didn't heat treat and we heat treated. Did heat treating matter? So here's what I'm going to do. Number one, remember, look within each level. Do I see any non-randomness? No, I don't. It's just common cause. I can use the average and standard deviation. There's what I can expect. I do the same thing over here. It's common cause. Now what I'm going to do is I'm going to compare the graphs and I'm going to say, okay, if I look and my process is stable doing this, following this predictable pattern, would I expect to see this from it? And hopefully you look at that and you say no, but here's what you're asking. Does set B follow the same predictable pattern as A, same distribution? No, it doesn't. Is the between difference in A and B random or caused by something special? Between here and here, I had this much variation here, I had a lot more down. No. Is the between difference more than I would expect based on the variation within A and B? It's all saying the same thing. Is this one population or two? And I think we can clearly see here it's two. Heat treating mattered. Okay, and just another way to look at it, we're saying, okay, if this is what's happening right here in my distribution, look, this guy is below this one and they don't even overlap. So it's saying, I'm doing this and all of a sudden I'm way down here doing this. No, that's not what happened at all. Okay, let's look at another example. Let's say our data turned out this way instead. So we look within here. Yep, that within, that looks random. This looks random. Then we ask, okay, let me look between. If my process is stable, would I expect to see data like this from it? And you're probably pausing because I'm saying like, okay, it's doing this. Would it be weird for it all of a sudden to do this? I mean, it's not like it shifted that much. Remember, things are random, they do change. And I'm like, yeah, that one's a little harder. Yeah, it is harder. Tool number one only helps with difference that's a no-brainer. I mean, here's what I'm talking about. When you have data sets that look like this, it's a no-brainer. That did not happen randomly. Or if you have something like this, that was not random. They're the same. I mean, that is random. They're the same. There's no difference between those. But as you start getting things where they get closer and they overlap like this, it's a little harder. This one, that's pretty clear. This one, yeah, those are probably different. But when they start getting like this, it's a lot harder to tell. We need another tool. And that's the second tool. And so what we're going to do is we're going to take this data and we're going to create an average. And then we're going to put a confidence interval on that average. And then we're going to look and see whether those confidence intervals overlap or not. And that's going to be the next video. So that's the first tool we look. And if it's a no-brainer, we don't necessarily need to go any further. If it's kind of not quite sure, then another tool we can do is we can put this confidence interval on it. And so that will be the next video that we'll go through.